Okay, folks, we're going to start dealing now with the factors that affect reaction rate, and you already know some of them, okay? And it should really be obvious that anything that would make collisions more frequent or would make them more effective collisions, or both, are likely to increase the reaction rate, okay? So that's the kind of the premise of any experiment that you do. You are using collision theory to explain the changes in the rate, okay? Now we're going to deal with concentration of reactants, and you already know about clock experiments. You measure the time taken for a certain point to be reached. We discussed that in a previous video, and you know that the average rate is inversely proportional to time, okay? It's proportional to 1 over time. If the rate is halved, then the time it would take twice as long to make the change, okay? And this experiment from GCSE, in those days, you found in your experiment that when you doubled the concentration of thiosulfate, the time taken was halved, okay? And that meant that the reaction was twice as fast. So you could conclude that in this particular reaction, the rate of reaction is proportional to the concentration of thio. And since we've got this blue equation here, average rate is inversely proportional to time, we can put 1 over time here, which is effectively a measure of rate. So I can put rate of reaction there, and you can see the rate of reaction is proportional to the concentration of thio, okay? And that was a little bit advanced for GCSE, but it's quite normal for IB. And now you can see that these are all different experiments, 1, 2, 3 experiments, and you've measured that one time. But since you've got this conclusion here, you can see that in one beaker or one test tube, as the reaction's occurring, the concentration of thio is falling. And since they're proportional, when the concentration's halved in that reaction, then the instantaneous rate would halve. So that gradient should be half of that gradient because the concentration is halved, okay? So the instantaneous rate at any moment in time, the instantaneous rate is proportional to the concentration of thio present at that time, okay? Here's another GCSE experiment. You produce hydrogen by the reaction of magnesium with HCl, and it changes the concentration of HCl, and then you get different rate curves. You've seen that all before, okay? In fact, you can visit the year 11 Firefly page and review it if you want to, okay? And it was very simple. In those days, we just explained it by saying if the concentration is higher, the frequency of collisions is higher, and so the rate increases, okay? And here we are again, still at GCSE level. You can see the reaction's fastest here, where the blue and the red are more concentrated. There's more chance of a collision, okay? And that was kind of pretty easy, okay? Now there are times when, at IB level, there are times when you change the concentration of a reactant and it has no effect on rate. Or there may be times where it's not proportional. It rises, but not in proportion, okay? So it's a little bit more complicated. Now, if you had this reaction here, at IB level, you'd have to find out how each reactant affects the reaction rate. You'd have to do individual experiments, find out how X affects the reaction, and find out how A affects the reaction. Now, of course, as the reaction's occurring, the concentration of both of them will fall. So they will both affect the reaction rate as it's happening. And so it's not very easy. So what you do is, if you want to find the effect, how A affects the reaction rate, you'd have to have the concentration of X 10 times greater than A. So that as the reaction occurs, the concentration of X is hardly changing as it falls. And what you are then seeing is really the effect of A, okay? So you need to find the effect of each reactant separately. If the initial concentration of X was 10 times greater than A, then any observed effects are due to changes in A as it's happening, okay? And then you could repeat the experiment with A 10 times greater than X to see the effect of X, okay? Now this person here has done an experiment where they are following the rate by following changes in A. You can follow it in any way you like, but they're going to follow it by actually measuring the concentration of A falling with time. And what they found is they've got the initial rate here, and then they're taking instantaneous rates by taking tangents to the curve. And look what they found out. They found that as this is not drawn to scale, by the way, this y-axis, but they found that as the concentration falls, the rate is falling in proportion. Okay, as the concentration is halved, then the rate is halved. Okay, the rate of the reaction, the rate of consumption of A, is proportional to its concentration. Okay, so we can write that rate of reaction proportional to the concentration of A, and I can write this little equation here. Okay, now what you could do is, you could, instead of having one experiment and measuring all those tangents, you could just measure the initial rate for several different initial concentrations. Just measure the initial rate, get the tangent, throw it down the sink, then start again with a different initial concentration. So here we are. We're going to start with this high concentration here, and we've got this rate, and then we're going to start again, but we're going to drop the initial concentration of A and see what the tangent is. Okay, so here we go, we'll drop it now. We've dropped it down to half, and look what we found. We found that when the initial concentration was halved, the initial rate is halved. You can see that's gone down there. Now we'll drop it again. Here we go, drop it, and we find that the rate goes down again in proportion to the concentration. So now again, you can confirm this relationship, and we can write that equation there. The rate is proportional to the concentration of A. Now I can write what's called a rate law, a rate equation, and I can say, I can get rid of this sign and I can put in a constant. Here we go. The rate is equal to some constant times the concentration of A to the power of 1, because it's directly proportional. I don't really need the 1, but exams, they often put that in. Okay. Now, the rate of reaction is measured as moles per dm cubed per time, per minute in this case. We know that this is moles per dm cubed, and this is called the order of reaction. It's the exponent in the rate law, and it's 1 because it's directly proportional. Now, I want you to pause the video and work out the units for this rate constant. Okay, pause the video now and work out what the units are for K. And it's maths, not chemistry. So you should be able to work it out by rearranging. Yeah, here we go. The unit of rate constant is per time, in this case per minute, because I have a minute there. But it's going to be per time, it could be per second, per hour. But the unit of a first order rate constant is per time, time to the minus 1. Okay? And now I can say the reaction's first order with respect to A. There's the exponent for a first order rate law. And here are all the relevant units in the rate law. Okay. Now, you will never see this in exam, but this is actually called a pseudo rate constant because it only concerns A. We haven't talked about X yet, right? So, but you'll never see that in the exams. Now, repeat the experiment, but for reactant X. And for this, you need the concentration of A to be 10-fold that of X. So any changes you observe must be due to X. All right, there we go. Concentration of A is much greater than X. Okay. Now the person, again, they're just going to use A as their measure of rate, and everything will be the same in the experiment, but they'll change the initial concentration of X at the beginning. And you can see that with this concentration, they're getting this initial rate, this tangent here. Now they're going to drop this here, see what happens. And look what happens. My goodness, we've changed it to this initial concentration, but the rate hasn't changed. Same tangent. Now we'll change it again. And again, the same tangent. So it looks like X has got no effect on rate whatsoever. Okay? The reaction rate is unaffected by changes in X, and that is contrary to what you learned at GCSE, where it was kept simple. Okay? And again, look, it's been dropped, and the initial rate is the same. So now I can draw this graph. As the initial concentration of X increases, the rate does not increase. Okay? Now I can change the axes here, and I can have time against X. And you can see that as X falls, the rate of its own consumption does not change. I have a constant gradient. I don't have a curve like I had with reactant A. Now obviously A is going down as well, but the changes in A are really, really small because it's in such high concentration. So this shape of this line is due entirely to changes in X. And you can see as X goes down, the rate is constant. And another way to do it is you can literally change the initial concentration of X. Look, initial concentration, and the gradients are identical. So the initial concentration of X does not affect the reaction rate. Okay, that's very important. Now I can write this equation. The rate is proportional to just X to the power of 0 because X has no effect on the rate. And the rate law would be written like this. That, of course, is moles per dm cubed. This, of course, is moles, this is moles per dm cubed per minute. This is moles per dm cubed. And this is the exponent 0. And anything to the power of 0, of course, is 1. Now, please pause and work out the unit of K. Okay, and you can see that because this is 1, the unit of K is the same as the unit for rate. Moles per dm cubed per time, in this case per minute. Okay, so here we go again. The exponent is 0 because it's 0 order, and here are the 3 units in a 0 order rate law. Okay, there you go. Now we can say that the combined rate law, the overall rate law, is rate is equal to the rate constant for the overall reaction times a to the 1 and x to the 0. And because that comes out to be 1, I can ignore it. And therefore, the overall rate law is rate equals k times a to the power of 1. Reactant x has got no influence on the rate. It's not included in the rate law. And the rate constant here is, of course, per time, as you worked out earlier on. Okay? Overall order is the sum of the individual orders, which in this case is 1. Okay? Now, this is the last slide for this initial introduction, this initial video on rate laws. And I want to get something into your head, and it's got to stay in there. Okay? The rate law has got absolutely nothing to do with the balanced equation. You cannot get a rate law by looking at the equation. And you can see, obviously, there's no X in this rate law, but of course it's one of the reactants. So again, there's no relationship between the balanced chemical equation and the rate law. The only way you can work out a rate law is by doing experiments. The order of reaction can be found only by experiment and bears no relationship to the balanced equation. Get that in your head, okay? And now I'm going to tell you what the chemist will do. What the chemist will do using this rate law. The chemist will now try to propose a mechanism, a theoretical mechanism for the reaction using this knowledge here. And a mechanism has a number of individual steps called elementary steps. And those elementary steps must add up to the overall equation, and the proposed mechanism must match the rate law. And I'll explain that now in a separate video. Okay? So this introduction here was just showing you how the rate of reaction is related to concentration. And it's not very simple because sometimes changes in concentration have no effect on rate, and sometimes they are directly proportional, and you're going to learn about other relationships between rate and concentration in the next video. Okay, so that's it for now. Thank you.